Hello, everyone. My name is Utpal Herat, and I'm a graduate student at the Department of Physics and Astronomy at West Virginia University in the research group of Dr. Aldo Romero. Today, I'll be talking about DMFT with DFT, which is an open source code to treat strongly correlated materials. This was developed in collaboration with Dr. Hyo-won Park's group at the University of Illinois at Chicago. First, I'll introduce what strongly correlated materials are. These materials lie in the transition metal and rare earth and actinide regions of the periodic table. What's remarkable about these materials is the localized nature of their higher order D and F orbitals. And this leads to a minimal overlap of their wave functions with neighboring orbitals, which in turn leads to prominent electron-electron interactions that cause these correlated effects. The correlations lead to intriguing properties such as metal to insulator transition seen in vanidates. This is the basis for smart windows, and high temperature superconductivity seen in cuprates, and colossal magnetoresistance displayed in manganates. And this is the property used in spintronics applications. Now, to see the source of these correlations, it all boils down to two competing energy scales, which are the hopping term, which is related to the kinetic energy of the electrons, and the screen Coulomb repulsion. Due to the interplay between these two parameters, materials behave as metals or insulators, but what we are interested in is this region in between that. And to study this interplay, the simplest model used is the Hubbard model, which consists of a kinetic energy and a potential energy term. But to study this behavior in a more subtle and in-depth way, we use the Anderson impurity model in our code, which treats the impurity embedded in a bath, which is related through a hybridization function. The most popular way to do first principles electronic structure calculations is through a method known as density functional theory, which is basically an approximate solution to the many-body Schrodinger's equation. And in density functional theory, we use approximations to treat the correlations. Now, DFT works well for weakly correlated materials, but due to the fact that we are using an approximate term to compensate for the electron correlations, it fails for correlated materials. For example, in nickel oxide, where DFT treats it, or DFT sees it as a metal, and in reality, it's an insulator. So to probe correlated effects, we need beyond DFT methods, and one immediate correction is to use the Hubbard U correction with DFT, but that only addresses the static localized limit. So to see a full dynamic picture that treats time fluctuations exactly, we use a method known as Dynamical Mean Field Theory, or DMFT, in addition to density functional theory. And we use the Anderson impurity model here, as seen in the previous slide, to do these calculations. Now, there are already existing DMFT codes, but in the next couple of slides, I want to show what the features of ours are. So the goal of the DMFT framework is to create something that is easily interfaceable to any DFT code and require a very minimal user input. So far, we have been able to interface our DMFT code with the DFT codes VASP, Siesta, and Quantum Espresso through the 1ER90 interface. And recently, our article got accepted to the Computer Physics Communications Journal. And it's written in languages of Fortran, Python, C++, which are parallelized with MPI. And here's a structure of the code. So the inputs are retrieved from the DFT and 1ER90 interface, which are then fed into the DMFT segment, which uses the impurity solver to retrieve the self energies of the impurities, which are fed back into the DMFT loop. And apart from the DFT inputs, tight binding Hamiltonians can also be used as the inputs here. Now, there are two main scripts that govern the calculation. And these scripts call other scripts and libraries that perform these tasks. And here I have some select outputs, which are the spectral functions, the DMFT partial density of states, and orbital projected spectral functions. Now, one of the main features of our code is its simplicity to use. Here I have an example to run a DMFT calculation for strontium vanadate using the DFT code Siesta. The only file inputs we need are the DFT inputs and a single file that governs the DMFT inputs. And using a single line like this, you can perform a full DMFT calculation, and then followed by this line here, which does the post-processing calculation to get a spectral function. So you can see how easy it is to run a DMFT calculation with this code. Here I explain the workflow that happens under the hood. So once the DFT calculation is performed, we have the cone charm orbitals, and then we need to project those into a correlated subspace using 1-year-90 to obtain the maximum localized 1-year functions. To find which orbitals are in the correlated subspace, you can use a code like Piprocar. And then once we have the 1-year Hamiltonians, we use a guess for the self-energy, which we feed into the DMFT segment. And that provides us with the hybridization function and the local Green's function, which are used as inputs for the CT-QMC code, which performs the impurity solver. And what we use here in our code is the impurity solver written by Dr. Howley in Rutgers. And the impurity solver solves for the Green's function, the impurity Green's function, and the new self-energy. And DMFT self-consistency is achieved when the impurity Green's function is equal to the lattice or the correlated Green's function. And this loop is done self-consistently until that convergence is reached. Once it's reached, one may do post-processing, or additionally, to reach full charge DMFT plus DMFT self-consistency, one can reiterate this complete loop through the DFT code, and to call the charge density, or to calculate the charge density of DMFT, one calls the DMFT with DFT library within a DFT code. And that results in a full charge self-consistent DFT plus DMFT convergence. Now here are some results we obtained. This is for nickel oxide, and DFT predicts it to be metallic, but in DMFT calculations, we see that the results show an insulating behavior. And that is in agreement with our PACE data obtained from experiments. Next, this is an example for strontium vanadate. Here you can see a DFT orbital projected band structure retrieved from Piprocar to see which orbitals are in the correlated subspace. And in the DMFT density of states, you can see mass renormalization effects that we can't see in DFT. And using the imaginary self-energies, we can calculate the mass renormalization. And we found it to be around 1.7 for the T2G states in this material. And looking at the imaginary self-energies, we can see that the Siesta and VASP results are very close to each other. And here are some spectral functions for different DFT codes. So the results retrieved for VASP, Siesta, and Quantum Espresso all are very much similar, and we can see these mass renormalization effects. So here's some current and future work. So we want to extend the interface to other DFT codes, which we're currently working on. And also another study we're doing is to see how oxygen vacancies behave in DMFT studies. And we're also working on force calculations and implementing the self-consistent Hubbard U and DMFT, and also studying F-electron systems with our framework. So in summary, I talked about some of the features of the DMFT with DFT framework. And here are some links you can get more information from. And I would like to recommend this talk by Professor Gabriel Kotliar that's going to happen on Sunday, because he's one of the pioneers in this field. And if you would like to learn more about correlated materials or DMFT, that would be a nice talk to attend. So thank you for your attention.